Hello friends, the history of the universe spans 13.8 billion years. It includes everything we know, see and experience. Even if there are parallel universes, we might never be able to observe or interact with them in a scientific context. The history of the Earth dates back 4.5 billion years. The earliest signs of life are from 4 billion years ago. This video will guide you to space and time, visiting the most important universal and earthly events and processes. These processes provide the resources and energy for life to start and evolve, as well as conditions for life forms to become extinct. At the end, we'll talk about the existential crisis us, the humans, are facing. Please consider your role in this story. Please consider your mission in the future of life, the universe, and everything. Fellow agents, welcome to the Space Travel Vlog. The period of 13.8 billion years is mind-bogglingly difficult to grasp. We can transform this incredible length of time into a cosmic calendar, which represents the history of the universe as one calendar year. The cosmic year starts on January 1 with the so-called Big Bang, which is the hypothesis that all matter in the universe was created at one particular moment in time. The year ends at midnight of December 31, which represents the current universe. Much of our home galaxy, the Milky Way, formed during the first months of the cosmic year. The solar system formed in cosmic September, which is roughly 2/3 through the universe's history. The Earth formed soon afterwards, and increasingly complex life forms developed through cosmic October and November. Multicellular life developed within the last cosmic month. The majority of fossils come from the second half of cosmic December, with the first vertebrates, land plants, insects, amphibians and reptiles evolving before cosmic Christmas. The last supercontinent, Pangaea, formed around Christmas, with dinosaurs, mammals, birds and flowers evolving in the following cosmic days. Most dinosaurs became extinct on December 30th. This event allowed mammals to take over newly available habitats and rapidly evolve into new species during December 31. Modern humans exist for less than 10 minutes, expanding globally during the last 4 minutes. All recorded human history has taken place during the final minute. The last ice age ended 25 seconds ago. Columbus kickstarted the colonization of Americas 1.2 seconds ago. The Industrial Revolution spread globally within the last 0.4 cosmic seconds. The Internet is less than 70 cosmic milliseconds old. Now, let's go back to the place and time where it all started, the Big Bang. It is the leading cosmological model explaining the evolution of the universe, including its earliest phases. The beginning of the universe was an odd moment because everything was packed densely at a very high temperature. Such a state represents a singularity where the known laws of physics do not apply. The Big Bang created time and space, or space-time, which has been expanding ever since. The early universe was a plasma soup of subatomic particles. During the first 370,000 years, the universe was too hot for atoms to form, but as it cooled down, the lightest atoms, those of hydrogen and helium, formed. Over time, they became ingredients for the first generation of stars, in which heavier chemical elements formed. All the atoms that make up who we are, what we see, and what we use as resources are recycled from stars, which themselves are building blocks of galaxies, as well as environments in which planets form. Looking far and deep into the universe is like traveling back in time, because light has a finite speed of nearly 300,000 kilometers per second in a vacuum. The cosmic microwave background is the earliest universe we can observe. This relic electromagnetic radiation is a remnant from an early stage of the universe. Due to the expansion of the universe, the wavelength of these once hot photons was shifted. Nowadays, they can be observed as microwave radiation. The image you see now is a combination of observations taken over 9 years by the WMAP mission. It shows temperature fluctuations of just plus minus 200 microdegrees on Celsius and Kelvin scale. The map is used as the universe's initial state, or its baby picture. If we plug it into cosmological models, we can predict and analyze the shape, content, and evolution of the universe. The most surprising thing about this map is that the slightly denser and hotter regions represented by red, yellow, and green colors are those places where the large-scale structure of the universe formed. Thanks to the formation of hydrogen and helium, the universe became transparent but dark because stars did not exist yet. During the first billion years, the first generation of stars formed, allowing the large-scale structure of the universe to emerge. While we can only imagine how the first stars formed, the large-scale structure is something we can observe today. This incredible simulation gives us an idea of what the universe might look like on the largest scales. Stars form into galaxies, galaxies into clusters, and clusters into superclusters, which are represented by brightest points on this three-dimensional map. Between the clusters and superclusters exists the so-called cosmic web. Those are long filaments of galactic material and dark matter that stretch through otherwise empty space. Now, we know some of the most important events in the history of the universe. The Big Bang, the formation of the first atoms from which the first stars formed. Stars and their systems play a critical role in the evolution of the universe. Not only do stars light up the universe, but they also generate chemical elements heavier than hydrogen and helium. Star formation takes place in a cloud of atoms, molecules, gas, and dust. The leftover material sticks together and accumulates, creating planets, moons, asteroids, comets, and other small bodies. Stars, together with interstellar gas and dust, stellar leftovers, and dark matter, form galaxies. A galaxy can have any number of stars ranging from a few 100 million to 100 trillion. The image shows our closest galactic neighbor, the Andromeda galaxy. It is approximately 2.5 million light-years from the Earth. By observing Andromeda today, we can see how it looked 2.5 million years ago, which is close to nothing given the age of the universe. However, if we look deeper into the universe, we can observe ancient galaxies that tell us the story of the early universe. This video shows a compilation of images taken by the Hubble Space Telescope when pointed towards a seemingly empty patch of sky. It took scientists by surprise when the original Hubble Deep Field in the mid-90s revealed thousands of previously unknown galaxies, some of the oldest and most distant known. Such a revelation completely changed the way we think about the universe. It is teeming with hundreds of billions of galaxies, each hosting millions, billions, and even trillions of stars. Such a universe, in principle, opens up nearly endless opportunities for places where life could form. But do other stars have planetary systems? Exoplanets are planets orbiting stars other than the Sun. Nowadays, we know thousands of exoplanets and even have indirect evidence of extragalactic exoplanets. Estimates for the Milky Way indicate at least one planet per star on average. The first exoplanet was confirmed in the early 90s, opening up a range of scientific fields for detecting and characterizing exoplanets, as well as researching the conditions for extraterrestrial life to form and evolve. Nevertheless, the Earth remains the only place in the universe where we know life exists. Finding life elsewhere is possibly the largest scientific quest of our species. The Milky Way, our home galaxy, is one of billions of galaxies. It consists of hundreds of billions of stars. We can clearly see the Milky Way when escaping light pollution on cloudless nights. For example, here in Tana Bog, not far from Riga in Latvia. What defines our daily lives by providing light and heat is much closer to home. It's the Sun. The solar system formed around 9 billion years into the universe's history. So, the Sun has been around during the last third of the full 13.8 billion years. Our home star formed from a massive interstellar cloud of molecules that collapsed under its own gravity. The leftover material formed the so-called protoplanetary disk, which in turn served as an environment for planets, natural satellites, asteroids, comets, and other small celestial bodies to form. The Earth formed during the early, most violent period in the solar system's history. The Earth is about 4.5 billion years old. Its geological history is shown on this 12-hour clock starting at noon, which represents the formation of the Earth. It is a very unique planet because it is the only known place where life exists. The first organisms that exist in the geological record are prokaryotes. The evolution of the Earth and life itself eventually led to development of complex species, including humans. The first prokaryotes formed as early as 500 million years into the Earth history, or around 120 on the geologic clock. After 0.8 billion years, at around 330 on the clock, some bacteria evolved a photosynthetic capability. This led to the Great Oxidation event at around 6 o'clock in the geologic clock. Soon after, eukaryotes evolved from which complex multicellular organisms developed starting around 8 o'clock. During the last 500 million years or so, the Earth has seen animals evolving. The Cambrian Explosion gave rise to almost all major groups of animals, including our own very distant vertebrate ancestors. The explosive development of new species happened within an incredibly short period of time, 20 million years. Homo erectus and other ancestral human species evolved and perished during the last 2 million years. The Earth and other planets have formed thanks to the process called accretion, during which molecules, dust, and meteorites gradually accumulate, creating a new celestial body. The early Earth was a ball of molten metal and stone covered with lava. The dense metals sank to the core, created the Earth's magnetic field about 10 million years after the Earth itself formed. The currents within the Earth's metallic core generate the geomagnetic field of the whole planet. This magnetic field shields the near-Earth environment from the direct impact of the solar wind and possibly reduces atmospheric erosion. This simulation from one of our earliest blog posts shows how the solar wind arriving from the right impacts the Earth's magnetic field represented by black lines. According to the giant impact hypothesis, the Moon formed from debris of collision between the Earth and a hypothetical planet called Theia. As we can see from the lunar surface, The early solar system was a messy place of planets, asteroids, and planetesimals crashing into each other. Later on in the solar system's evolution, gas giants such as Jupiter cleaned up the system. This happened thanks to planetary migration, which is the change of orbits causing planets to move closer to or further away from the Sun. The main belt is an exceptional region in the solar system where ancient asteroids still tumble around the Sun. Our beloved companion, the Moon, not only guides us through the darkest moments, but also helps to stabilize the Earth. Life does not like wobbly planets, because their climate swings are large. The Moon improves the conditions for life because it stabilizes the Earth's rotational axis and therefore the seasons and the climate. The early Earth, which is considered to be the period of the first billion years of its history, was a rather different place. The atmosphere had extreme amounts of CO2 and only trace amounts of oxygen. Water existed in vapor and probably cloud particle forms. Since the Earth formed as a hot lava ball, then liquid surface water, if there was any, would have immediately evaporated in the atmosphere. So why on Earth are there oceans full of water? The comets are the first obvious candidates for water delivery to the Earth, because we can see their water-rich tails light up as they approach the Sun. However, as the European Space Agency's Rosetta mission showed, the water on the comet 67P is not quite the same as that on the Earth, because it contains more heavy hydrogen than expected on the Earth. This also holds true for other comets. The next, less obvious candidates for water delivery to the Earth are asteroids. Asteroids are seemingly dry objects covered with dust, which is also known as a regolith. Regolith is created by space weathering. It's a process of micrometeorite impacts and thermal cycles that breaks down surface rocks on planetary bodies exposed to hard vacuum. Here we can see a map of the dwarf planet Ceres, indicating an underground ocean discovered by NASA's Dawn orbiter. Indeed, the ratio of hydrogen and helium in the water of asteroids matches that of the Earth, making asteroids and planetoids the best candidates as sources of water on the Earth. Some fraction of water on the Earth might come from water trapped in the original planetoid. Asteroids may well have delivered the rest. Apart from space weathering, asteroids have remained unchanged since the early solar system formed, which in turn makes them excellent targets for understanding the early solar system. What do we know about the Earth thus far? It formed early in the solar system's history. The molten metallic core generates the geomagnetic field. The Earth was bombarded with planetary bodies of varying sizes, which possibly created the Moon and brought water to the Earth's surface. For nearly 2 billion years, single-celled prokaryotes ruled the world until the Great Oxidation event, which took place 2.3 billion years ago at around 6 o'clock in the geologic clock. Cyanobacteria are the first organisms known to produce oxygen. During the Great Oxidation event, oxygen produced by cyanobacteria overpowered the reductive capacity of the Earth. This led to the accumulation of a large amount of oxygen in the atmosphere and the oxygen-rich atmosphere we know today. The image you are looking at now shows how a bubble of oxygen emerges from a cyanobacterial mat grown in the lab. The production of oxygen by living organisms was a seismic shift for life on the Earth, because oxygen was toxic to all life present at that time, and organisms had to either adapt to oxidative stress, migrate to anoxic regions, or suffer extinction. This is an example of habitability being temporary, at least for those ancient prokaryotes, because the oxygen-rich atmosphere created an environment where eukaryotes emerged and evolved into all known complex multicellular organisms. The Cambrian Explosion was another major event for life on Earth. A mere 20 million years were enough for the predecessors of a large proportion of modern animal life to develop. New developments included hard body parts such as shells, skeletons, and exoskeletons. These hard body parts are the best preserved fossil material we can find today. The image shows a tiktaalik fish fossil that is about 375 million years old. Scientists think that such fish, whose fins help to prop the fish up in shallow water and move about on shallow river beds, are the predecessors of four-legged vertebrates such as amphibians, reptiles, birds, and mammals. In order to give a perspective of the geological age of the Earth, here is the Sietiniesis sandstone formation in Latvia. It is some 400 million years old, which is around December 18 in the cosmic calendar. Around 200 million years ago, which is half the age of Latvian sandstone at Sietiniesis, all Earth past and future continents were assembled into a single supercontinent called Pangaea. The world-famous Delicate Arch in Utah is made of rock that is 160 million years old. Up until 66 million years ago, the Earth was dominated by dinosaurs. According to one theory, a large asteroid impact near what is now Mexico created an environment impossible for dinosaurs to survive in. If earthquakes and tsunamis were not enough, the Earth's atmosphere was filled with dust for several years, creating a harsh environment for living things. The extinction event that led to the disappearance of the dinosaurs is one of 5 major extinction events that are believed to have happened in the Earth's history. So much about extinction. How did it all start anyway? No one knows how life formed, and no one has been able to reproduce the life formation process in the lab. However, we know life can exist, survive, and thrive in extreme conditions. For example, 2 or 3 kilometers down the ocean floor, and sometimes at greater depths, there are hydrothermal vents around which the temperatures often exceed 100 degrees Celsius and there is no oxygen. But yet, we can find microorganisms there. To some extent, conditions at hydrothermal vents sound like conditions of early Earth. One of life's great survivors is the tardigrade, which has been famous among scientists who have tried to kill it by exposing it to vacuum and ultraviolet radiation of low Earth orbit for 10 days. However, some tardigrades were able to survive this challenge. They have also survived for 30 years in minus 20 degrees Celsius, several minutes at 150 degrees, as well as at minus 270 degrees Celsius. On top of that, some scientists have taken tardigrades for trips 4 kilometers below sea level, which some of these tardigrades and all scientists survived. While we have little clue as how life started, we can define the requirements for life to start and evolve. We need a source of energy, which can be solar, thermal, or chemical. Liquid water and carbon are irreplaceable ingredients for life as we know it to form. Some form of nutrients are required, as well as a relatively stable environment for life to adapt to. Various factors define habitability. For example, for the Earth, the ozone layer protects us from the ultraviolet rays. Plate tectonics help to recirculate sediment. A circular orbit around a host star and the existence of a natural satellite stabilizes the environment. A sufficiently rapid day-night cycle prevents locations from excessive heating and cooling. The image you are now looking at shows planetary habitability, which is defined by a habitable zone around a host star where liquid water can exist on a planetary surface. We can, however, look for life outside the habitable zone. For example, Enceladus has a global ocean and its geothermal activity creates geysers. NASA's Cassini mission found traces of simple organic compounds in the geysers of Enceladus. The recent unexpected detection of phosphine in the Venus's atmosphere adds to the existing speculation on the possibility of life in clouds of Venus. On Earth, phosphine is only associated with life and no other abiotic geological process makes phosphine. As of now, phosphine is considered a biomarker and further investigation is necessary to say anything about its role on and around Venus. Now, let's make a leap forward and look at humans, whose evolution spans the last 2 million years. and who appeared on the Earth during the last day of the cosmic calendar. We evolved from apes who developed the ability to walk upright. The brain size increased rapidly as humans evolved and Homo erectus learned to control fire. The modern human, also called Homo sapiens, originated about 200,000 to 300,000 years ago in Africa. If you take a closer look at this image, you can see how Europe might have looked during the Ice Age. Just 11,000 years ago, the last Ice Age ended, uncovering large, nutrient-rich lands in the north, while submerging many previous human habitats underwater and forcing mass migration away from now uninhabitable areas. Humans were able to expand, for example, into northern Europe, which was mostly covered by young forests, swamps, and grasslands. Towards the end of the last Ice Age, some 12,000 years ago, the first signs of the agricultural revolution are evident in the historical records. The scientific revolution took place during the 16th and 17th centuries when Isaac Newton developed modern physics and mathematics, when Francis Bacon developed the scientific method, when Nicolaus Copernicus placed the sun rather than the earth at the center of the universe, and when Galileo Galilei invented the telescope. The father of capitalism, Adam Smith, published his most influential works in the 18th century. The Industrial Revolution went full steam ahead in the second half of the 19th century. We believe these are the events defining our modern life. The way we eat, the way we develop technology and explore the universe, and the way we use technology for economic gain. But how far can we go? In the name of prosperity and economic growth, we are burning fossil fuels and releasing carbon into the atmosphere. CO2 and other greenhouse gases are warming up the planet. We, the human race, are responsible for the global surface temperature increase. We are responsible for the extinction of species and the reduction of biodiversity. Most importantly, we are hurting ourselves. The Earth will be just fine. As you saw today, the Earth has seen worse. It is rather the factors that make the Earth habitable and requirements for life that are changing. In particular, the requirement for a stable environment is no longer being fulfilled. By dumping greenhouse gases into the atmosphere, we have created the world out of balance, where extrasolar energy is captured by the Earth's system. More so, we have taken over and affected nearly all natural habitats. The UN's panel on climate change calls it the climate catastrophe. A catastrophe is an event causing great and usually sudden damage or suffering. Most of the world's population is already experiencing this suffering during heat waves, floods, storms, and other extreme weather events. What can we do in an attempt to mitigate this suffering? First and foremost, we should make sure that the Earth is habitable for as long as possible. It is by far the best place for humans to live. We should research the formation of life in order to understand the fundamentals of biology. We should explore life, the conditions it needs, and habitability outside the Earth. Because sooner or later, the Earth won't be the best place. We need a plan B, so let's prepare for the expanse outside the Earth. Dirty Deal Audio, Oriole Beats. Paldies, Antti. Mana ceļa gals ir spirāles centrs.